On example 3 in your handout for chapter 6, I have a drawing there of a stick figure in the middle of a kind of like donut looking thing. If you look on this screen here, that's actually the donut looking thing I was trying to replicate. So this was a concept idea by NASA in 1975, and it was, how do we overcome weightlessness so we can have people in space longer? And then the idea was that if this little tube looking thing rotated at like 1 rotation per minute, it would mimic the acceleration due to gravity. And that would allow us to have these big, beautiful cities. I don't know if that's a swimming pool, but all of these things would stay put, and you would be able to live in this big, beautiful city with 10 to 140,000 of your closest friends. So going back then, to my beautiful drawing, here is my stick figure. So it's a different spot, and my circle's not quite as nice as the one I made on the computer. But we want to know if this one is 1.1 kilometers, I think NASA's was 1.8 or something like that. How fast will it have to rotate? How many revolutions per day will it need to achieve in order to get there? So let's see. This is the diameter. We need to change diameter into radius. So diameter is 2 times r. So 1.1 times 10 to the 3rd divided by 2 will give me my radius. There. Do that right out of the gate. That way, when you start doing your math, you use the right term instead of something that you don't intend to. So let's see. Before, in the previous videos, we defined that the force due to gravity is Gmm over r squared. And what we want here is for this then to become, let's see, this would equal mv squared over r. Well, this wants to know what we would have to do, to get A, which is this piece here, to equal 9.8. So let's see if instead of going this route, we can set this up and we can say, so our center seeking acceleration needs to equal v squared over r. So I know what I want this to be. So I want 9.8 meters per second squared to equal v squared over r. And why did I go here? Well, I started writing out my force of gravity equation, and I thought to myself, do we need these pieces? V squared over r, well, I know that that is going to come out to be g. That is my center seeking acceleration, my acceleration due to gravity. So remember, on Earth, we were doing mg, right? So we don't need to do all this other stuff. So I look at this then, and I say, okay, so let's see. I know this, but it wants in terms of revolutions per day. So velocity is 2 pi r times f for frequency, or divided by period. I'm getting close. I can rewrite a equals and then square all of that. So 4 pi squared r squared, whoops, divided by t squared. And all of that is divided by r. So these r's are the same. Let's clear this up. But I have 4 pi squared r squared divided by t squared r squared. I'm sorry, just r. So this r is going to cancel out, and that's going to cancel out. I have a, I want t, so I'm going to move t to the other side. So I get t equals 4 pi squared r divided by a. So here, this r is the radius of rotation. We're trying to mimic gravity using this rotating thing. And so I can put my numbers in here, that 4 pi squared times this r, which is 1.1 times 10 to the 3rd divided by 2. all of that divided by A. We want that 9.81 meters per second squared. So I crunch that out, and what do I get? I get that it's rotating 47, it takes 47 seconds to rotate. So this one is just slightly more than 1 per minute. So this whole answer is 47 seconds is the period. So this is how much time to complete one rotation. It's taking just slightly less than a minute to complete each rotation. So from that, I can jump into how many rotations per day, right? And there we have to do all sorts of things as far as how many seconds per day, or because you're online, you put things in, you can go, so I can write it out, 60 seconds in 1 minute times 60 minutes in 60 minutes in 1 hour, sorry, I lost my train of thought there, times 24 hours in 1 day. 1 day, there we go. I crunch all those things out, and what I'm actually answering with this one is how many seconds in 1 day. Or I type into Google and I say, Google, how many seconds in 1 day? And Google tells me that there are 86,400 seconds in a day. I get the same thing. I put those numbers together, multiply them together, throw them into my calculator, and I will get that. So let's think what that means. So this is how many seconds in 1 day. It takes me 47 seconds to complete one rotation. And I'm emphasizing this because the first time I did it, I put this in and I started converting to per 24 hours to get to the per day, which meant this was all flipped. And while it is giving me an answer in terms of days, which is good, it is giving me rotation. In one rotation, what fraction of a day do I take to get there? So let's just make sure we're solving for the same thing. So this top value does indeed give me how many seconds in a day. This is how many seconds, and that's how many seconds of that I'm going to use per rotation. So then it's just division. So how much is that? 86,400 divided by this 47 seconds tells me that it's got to rotate 1,838 times a day. And if you're wondering why this didn't happen, it is values like this that created issues. Then there were some physiological things that had to do with that kind of rotation in the human body, and then they weren't real sure if that would be a bad thing, and it would be really expensive to get there to even test the concept. Not to say they've abandoned it, but that just gives you an idea of think of how much energy it would take to generate that kind of rotation. So there's that.